Questions 43 through 44. A wheel with rotational inertia. I is placed on an axle and is free to rotate without friction. The angular speed omega of the wheel is increased from 0 to omega final in a time interval t. 43. What is the average net torque on the wheel during this time interval? So we know that net torque equals moment of inertia times angular acceleration. And we know angular acceleration is equal to the change in angular velocity over the change of time. Angular velocity is final angular velocity minus initial angular velocity over a change of time. And if we we increased it from 0, this term is 0. So angular acceleration equals WF over time. So we can plug that in here, and we're going to get net torque equals moment of inertia times angular velocity final over time. Number 44, what is the average power input to the wheel during this time interval? All right, so we know power equals work per unit time, and we know work is equal to force times distance parallel over time. The rotational analog to force we know is tau, and the rotational analog to distance is angular displacement all over time. We also know that tau is equal to moment of inertia times acceleration, so we can put that in there. And what else? So we know that we have to get rid of this theta. So we can say, okay, angular velocity is a change in angular displacement over time. So angular displacement is equal angular velocity times time. So let's plug that in for theta. No, let's roll that back. Yeah, let's get rid of this angular acceleration alpha first. So we know that angular acceleration equals the change in angular velocity over time. So let's put that in there. So angular velocity over time, so this becomes time squared. And this angular velocity is final minus initial over time. And since we started at 0, it's final angular velocity. So now if we can get rid of that theta by going back and using this, we would have moment of inertia, angular velocity times angular velocity times time all over t squared. This t and this squared would disappear, so we're left with something that looks, whoa, we lost All right, so let's see, what are we coming up with? It looks like we have moment of inertia times final angular velocity. So let's rewrite this over here. So we have power equals moment of inertia from here, angular velocity times angular velocity, so that's final angular velocity squared all over t. The closest I'm getting is this without the 2.